Hi there, everyone. Welcome to the live stream. I hope you can hear me. Just give a shout out in the comments if you can hear the audio all right, and I'm perfectly audible. So I will just wait for even the first comment to go through, and then we will go forward with the live stream. All right. So we got our first comment. All right. So welcome to today's stream. Today we are covering autoencoders in Tensorflow and how they are implemented. First of all, just a very short intro of GDG Cloud Islamabad. GDG Cloud Islamabad Google Developers Group is Cloud Islamabad is a group of developers that actually helps bring together the community of developers and help them integrate with each other, help them network with each other, and learn from each other's experience, as well as collaborate with the people that are working on Google technologies, as well as those working within Google to develop those technologies. So without further ado, let me introduce Imran. Imran is a GD in machine learning, and currently he's working at Red Buffer as a machine learning engineer. So let me add Imran to the stream. Hi, Imran.
Hey.
Hi, Imran. How's it going? Can you hear me all right?
Yeah, I can hear you.
All right. All right. So let me hand it over to you. If you can share your presentation. Yeah, I think we can see it.
Yeah. All right. So should I start just now?
Yes, yes. Please kindly share your presentation, and then I will give you the floor, and then you can take it over there.
All right. So for now, it's more of a guide and a tour of autoencoders. And by the way, thank you for the introduction, Krishan.
Yeah, let me remove myself from the stream, and then you can take over.
All right.
All right. Over to you, Imran.
Thanks. Assalamualaikum. Acha. So today we're going to discuss about autoencoders and how we can code them. And exactly, so we're going to ask ourselves three questions: what are they, how do they work, and why do we need them, right? So instead of going the conventional way of slides and presentations, I'm going to actually follow a blog which I actually wrote. So I'm going to just start right now. So basically, in machine learning or in this particular field, there are two major types of tasks. One of them is a discriminative task, and the other is a generative task. Now, in the class of discrimination, you usually have your regression models, your classification models, or anything you want to discriminate from each other. So, for example, in classification, you're discriminating against cats and dogs, for example, or in regression models, you're actually discriminating some value. For example, in a very famous problem for the Boston housing, you actually discriminate the prices of the houses. So that's how discriminative model works. But the other part of machine learning is generative modeling, and this is what I specialize in. In generative modeling, your goal is not to actually discriminate between the data. Your particular goal is to generate the data from the data, right? And a particular example we see in conventional machine learning is PCA, principal component analysis, where what we do is we take some data and we generate some other low dimensional data from the component, right? Just like PCA, we have another class of generative modeling, which is mostly used in computer visions. Actually, it is used in NLP too, but usually it's used in computer vision, right? And this class is called autoencoders. Uh, Autoencoders is not particularly a direct branch from machine learning. It's a branch of I'd say deep learning, because it has to have more than one layer in in the network. And before I go or dive into this autoencoders, I'm going to just notify you guys that I'm not going to teach you how neural networks work, because it's sort of a prerequisite for this particular guide, right? So so basically, what exactly is an autoencoder, right? An autoencoder is basically a type of network, a type of deep learning network, or a neural network, where you generate your data from the given data, right? Uh, okay, so let's dive more into it. This is a particular example of a very small autoencoder, right? It's a neural network where the shape is like a like an hourglass, right? Now, this particular before I dive more deep into it, there are two main components of an autoencoder. One is the encoder part, and the other is the decoder part. Now, the encoder part. Okay, let's go more. Let's understand what the encoder part is. Now, as we've talked earlier about the PCA, the job of PCA, principal component analysis, is to uh, reduce to dimensions, or to make. Okay, I'll give a better analogy. Uh, if you have a picture of a cat, and is a for example, say 300 by 300 width and height pixel image with 3 channels. Now this is a picture of a dog or cat, right? And I need some particular way to represent this particular picture or this particular information in in a smaller or more compact way, right? Right. So for example, I'd say this particular image can be represented, this particular 300 by 300 by 3 image can be represented in let's say 10 by 10 by 2 image, right? Or a tensor, right? So the part of encoder is to compress or compress the image or the information or the data that we have into a smaller, denser representation, right? Now, this is the encoder. Now, there's another part here, which is the decoder. Now, from the input to the code that we have, the bottleneck that we have right here, it's the encoder. And the other part is the decoder, which uses that compact, dense information and generate the output for the particular input that we've given in the encoder layer, right? So what the decoder layer does is that it takes the output of the encoder and then regenerate that particular input to an output which is actually similar to the input, right? Now, if you're going to think about it, let me put it this way: it does not make any sense, right? You're just giving an input and you're generating an output, and they're both the same things, right? Because their size is the same. So what's basically the whole point of an autoencoder? That's a question, right? So let's go into the purpose of the autoencoder. The real and the main purpose of the autoencoders is dimensionality reduction, which we do in this bottleneck layer, which the encoder does. So what does the decoder do? The decoder part is used to generate from that from the decoded compressed dense representation to another uh, to another to an output which is somehow basically the same as the input, right? And the compression, it depends on the kind of network you use, the kind of the kind of layers you use, or in the convolutional neural networks, the kind of kernel size you put in, right? So so the compression part, it depends on the type of network that you have, right? And this particular middle layer, which is the compressed information, is also called the bottleneck layer, right? Now, there are when we go into the practice of autoencoders, there are basically well, in the case of computer vision, there are two main types of autoencoders. The first one is the fully connected autoencoder, or we also call it the dense autoencoder. The reason behind the name is pretty obvious, because it uses all the dense layers or the fully connected layers. The fully connected layers are the simple layers that you use in the neural network. But the uh, the idea is to in the encoder part reduce the dimensions, and in the decoder part, then from the reduced compressed dimensions, we're going to generate an output, right? So there are I've added some code for this, and we're going to go in the code, but I'm going to finish this particular guides, and then we're going to move towards the code, right? So I'm going to skip this code part because we're going to do it later on, right? And all of the code is in TensorFlow 2 or 2x 2.x, right? This is the whole code. We're going to skip that. We're going to come back to it later when we're going to code it. Okay, so the next main part is convolutional autoencoder. Now it's just like a simple convolutional neural network with two main components: the encoder and the decoder. The encoder part, it now the encoder part, it does a very similar thing that it does in the fully connected autoencoder, which is it encodes the information. Now we're going to use a kernel size, and we're going to use a particular kernel size, not particular kernel size, any kernel size, to reduce the dimensions, right? So if you see in this figure, where is the convolutional third layer, the size is 3 cross 3 cross 1 cross 28, right? Which we project into 1152 of a vector of 1152, right? And then there is the bottleneck layer, which has a vector size of 10, right? And then another, and then after that, there is a deconvolutional or upsampling happening in the um, in the decoder part, which upsamples it to the exact the input that we have given, right? And we're going to train it. Now what's going to happen is that this particular input, when we start training, it's not going to generate this particular perfectly fine input that we've given. At first, it's going to give you garbage, then it's going to train. Now, all these layers are going to train, and then at some particular point, at some particular epochs, the result is going to be very similar to that of the input, right? And this is basically the whole point of autoencoders. Um, Right. And then there's another implementation of this convolutional neural networks that I've written in TensorFlow 2, and we're going to go that into a later stage. We're basically going to go into the code part at the end of this guide, right? And this is the entire convolutional autoencoder training code, and this is the training loop as defined here. Now there are some types of autoencoders. If you see in this particular picture, you can see that the input has some particular noise in it, right? It has so it's not very handwritten, or it's not very neat. In if you notice carefully, it isn't very neat, right? So there are like this sort of stuff is happening right here. So what the autoencoder does, the generation part is going to be a very smooth and denoised image. So one particular use case of an autoencoder is that uh, with the whole encoder and the decoder part is to remove noise or to denoise an image or denoise the data, right? So that is actually that isn't the goal. That is a byproduct of the autoencoders, which is really nice to have, right? Right. So when we talk about autoencoder types, the first type is the denoising autoencoder, right? And also I've written a code for the denoising autoencoder, and you can see that the only thing that we're doing here is basically we're just adding some noise to the input, and we can see in the output that this noise we will see in this output that this noise will be removed. And this is one example of, or the one type of the autoencoder, which is the denoising one. Now we're going to step into the most important part of the autoencoders, which is the variational autoencoder. Now, the problem with autoencoders is that they don't produce results in the decoder part if the compressed representation makes no sense. How does it makes no sense? For example, I've trained this autoencoder on a convolutional autoencoder on cats and dogs images, right? So once it's trained, I give it a cat image. It's going to generate a cat image, right? That's the point. But what if I give it an elephant image, right? What if the compressed representation is of an elephant or a car? We don't know that, right? Could be anything. The bottleneck layer here could be this dense representation could be of anything, right? So what we need to do is we need to have a certain way so that we only sample from the compressed layer, which is from the distribution of the training data, right? How do we do that? How do we cater for the distribution? Now we know that we define a distribution by it's simple. We define a distribution by its mean and standard deviation. So what we do, instead of having this bottleneck layer, we will have two components, right? We will have two components. We will use the mean and standard deviation, and we will sample from it, right? So let me put it this way: if you have a search space, your if you have a search space, your compressed information is only going to sample from the mean and standard deviation of the distribution, right? So so, so you're always going to get from that mean and standard. You're always going to get from that particular distribution, right? The decoder part is always going to get from that particular distribution. So as I've written here, we're just going to sample from the mean, which is called the mu, and the standard deviation sigma. But so there's a little bit of trick here. Now we have to train it. How do we train this mu and sigma, right? So what we do is it's pretty simple. What we do is that we add a simple standard Gaussian with zero mean and one standard deviation, and the equation looks very simple: mean plus standard deviation times sigma. Where and since it's a distribution and we're going to sample from it, so we have to make this mu the mean and the standard deviation learnable parts. right? And since it's going to be since we're going to compare the distributions in the output layer, we have to use some sort of different loss parameter, right? In above all these autoencoders, what we were doing was we were using a mean squared error loss. Now we cannot do that. We have to use some particular loss function that compares the distributions. Now these distributions are could be these loss functions could be anything. One particular is KL divergence loss, right? Uh, and we use that with the mean squared error loss, right? Because we are now comparing distributions, right? Uh, I have also written that the variational autoencoders are just like GANs, because essentially they're doing the same thing. They're sampling from a particular distribution, right? GANs does the same thing. Uh, their working is sort of different. Their network shape is different, but essentially they're doing the same thing, right? And I've also written the code for convolutional variational autoencoder in TensorFlow 2, and we're going to jump into that later, right? Training loop is the same as all the other autoencoders, and basically this is the end of the guide. Now what I'm going to do is that I'm going to jump into the autoencoders code part, right? I'm going to open my GitHub and I'm going to jump into that. Okay, so I have a lot written on the part of this generative part of computer vision. As you can see, we have style transfer, we have autoencoder, we have variational unit, which is sort of like an autoencoder, but the output is more of a label uh, than the data itself. I have written super resolution again, but what we're going to see today is autoencoders written in TF 2.0, right? And what I have written is simple autoencoders, denoising autoencoders, and variational autoencoders, all made in TensorFlow 2, right? And I've also given my Medium blogs link here. There are 4 files: the fully connected autoencoders, convolutional denoising autoencoders, and the convolutional variational autoencoders, all written in TensorFlow 2. So let's start with this very basic one, the fully connected autoencoders, right? So since the whole of the code is written in TensorFlow, and I've written the code in such a way that it's easier to read, and it also uses the eager execution mode of TensorFlow 2, which is a super cool feature to have. So I made a class of fully connected autoencoders, which is a derived class of Keras models. Okay. So when I'm going to define my layers, I'm going to show you how I actually made the encoder part and how I make the decoder part, right? In the first particular layer, you can see that I flatten the input. Now, since it's a fully connected autoencoder, we have to flatten the input because the input could be an image, a 3-dimensional image. It could have uh, a 3-dimensional image, for example, say a 300 by 300 by 3 RGB image, right? So I have to flatten it because I have to make my fully connected autoencoder work. I have to make my dense layer work, right? So my first layer is going to be a flattened layer. I'm going to flatten it. The second layer I've added is the encoder part. If from the encoder part is a dense layer with 64 neurons, right? So what's going to be the output of this particular layer? It's going to be a 64 neuron output, right? And I've also added an activation here, which is the ReLU activation. But activation basically is what it does is it makes your linear function non-linear, right? So if there's a dense layer, there's it's it's embedded by another activation, which I particularly chose as the ReLU activation. The next layer, I'm going to see, if you see this, I'm going to uh, minimize the number of dimensions. So in the next layer, I've given the dimension of 32, right? And in the bottleneck layer, my my neurons, they compressed from 64 from the first layer to 16, right? So this is the bottleneck layer. This is my dense representation of this input, right? And I've also uh, in com- I've also added an activation over it. Now, if you can see, the the next two layers, this dense 4 and the dense 5 layers and the dense final layers are what? If you can see, they're going to increase. The decoder part is going to increase the dimensions of the bottleneck layer. So it basically makes an hourglass shape of the network, right? And this here is the final layer, which is going to produce an output of 784. Now, how did I stack those layers? The first is the flatten, then dense 1, dense 2, bottleneck, goes to compressed representation, then this dense 4, which increases the size of the bottleneck layer, then dense 5, which takes the input of the dense 4 layer and increase it much more, and then there's the final layer. And I've what I've done is I've uh, returned the output and the reshaped part. I'm going to show you why I also returned the reshaped part, right? The loss function I've written is a simple mean squared error loss because it's not a variational autoencoder. Now here's uh, uh, the main training part, right? What it does is it takes the input. It's a gradient tape. It takes the input, it gives you the reconstruction and the inputs. I'll show you why I need them, and then I'll show, and then it goes the output and the input. It goes in the loss function because it's going to compare itself with the input. It's going to it's going to compute an error from the input and the output, which is the loss value. And then what's going to happen is going to train on that particular loss function, right? And optimize the weights. What weights? The dense 1, dense 2, bottleneck, dense 4, dense 5, and the dense final, right? And here's the main training loop. In the main training loop, what I've done is I've loaded the MNIST data, which is the X train. I've loaded the X test for the testing part. Uh, I've mean normalized the train and the testing part both. I've initialized the model. So I'm going to use the optimizer, Adam optimizer. You can use any choice of your optimizer. You can use the SGD, you can use uh, RMS prop, you can use Adam, you can use Ada Delta. I'm particularly using Adam because I feel like this is going to work better. The learning rate here is 0.001, 1e negative 3. Uh, and the number of epochs, the number of times it's going to go over the entire data set is 50. And the batch size is 4. Batch size is basically the number of example it's going to take in a particular step to compute a particular step. Sorry. So for each epoch and for each and for the batch size of anything you've chosen, is going to compute gradients over that particular loss function, and then the optimizer is then going to apply those gradients back to its to the weights, and that's how the training is going to happen. Now this particular autoencoder, the fully connected autoencoder, is a very simple type of autoencoder. As you can see, I've explained it very easily. It's basically just a 5-minute wrap up of the entire implementation, right? Uh, then we're going to move into convolutional autoencoders. right? And so I'm going to explain this convolutional autoencoder, and then the denoising convolutional autoencoder is going to be very simple. It's just going to be a small delta on top of it, right? Uh, so let's make a class of this convolutional autoencoders, and let's see how this particular convolutional autoencoder works. As you can see, in this particular autoencoder, this particular part is the encoder part. These first five layers are the encoder part. Then there's the bottleneck layer, and then there's the decoder part. Now notice there is no flattened layer here. Why? Because it's a convolutional neural net. In convolutional neural net, you don't need to flatten your input to a particular vector because the kernel is going to convolve over your over your input anyway. So you don't have to flatten the input, right? Again, the first layer is a convolutional layer, which is basically it has a 16 kernel size and an activation of value. The padding is the same. Oh, sorry, 3 by 3 kernel size, and the output is going to have 16 cross 16 tensor, cross 16 a tensor of 16 16 channels, right? And then there's the max pooling layer. So max pooling layer is pretty simple. What it does is that for a particular kernel, it selects the maximum from that it selects the maximum from that particular kernel size, right? So what it does is basically reduces your dimension, right? So until here, until this encoded part, what we're doing is essentially we're downsampling our input, right? And in this particular decoder part, you can see we don't have the max pooling layer. We have the upsampling layer. What it does, instead of downsampling like a normal convolutional layer, it upsamples it, right? It upsamples it. So what's going to happen is that it's going to compress the information till this encoded part, and then it's going to and then it's going to upsample the uh, upsample the input to the output, which is basically the same as the input itself. And now let's see how I've stacked them. So first is the convolution one layers, the max pooling one, these particular two layers. It's going to go like that until there's an encoded layer, which is the bottleneck layer. Then I'm going to start upsampling it, which is the decoder part. It's going to upsample it. Loss again is a mean squared error loss. Gradient tape is essentially and exactly the same as uh, in the fully connected auto layers part, but the training loop is sort of different. In the training loop, again, I'm loading the MNIST dataset, mean normalizing the train and the test, converting those train and test into a particular type, which so we can send it to our model. Dimension to We convert it to particular dimension, so we can send it uh, to the model, right? Which is basic. So basically, an MNIST data set has the input dimension of 28 cross 28 images, and the number of examples is the length of the training data set. And then there's only one channel because it's not an RGB image; it's just a one channel image. It's a grayscale image, right? I've initialized the model to convolutional or net autoencoder class. I made an object of the con net autoencoder class, which is defined here, which is I just explained. Uh, the optimizer is again Adam. I used it before in the fully connected auto layer part. I'm not going to change it. The number of epochs is again 50. Batch size is 4, and the training loop is again the same as that, right? So the only difference was here, right? So we're only difference was we're not going to flatten this input, and the rest is the same, except that it's going to use the convolutional layers instead of the dense layers, right? Uh, Okay, and then I compute the loss, and over that loss, I apply my gradients using my optimizer, and then I'm going to optimize the weights of those kernels. In convolution neural, we optimize the kernel parameters, and that's how we're going to train this convolutional autoencoder, right? Now let's move on to the convolutional denoising autoencoder. Exactly the same as the convolutional autoencoder with just one difference. The difference is in our training loop, after me normalizing the training and the test data set, and then changing their shapes to whatever we like, what I add is a noise factor. I add a noise factor to my inputs. That's it. That's basically it. And what I do in the clip by value is basically I clip it from 0 to 1. So if I add a noise, so in the grayscale image, it should be from the pixel value should be from 0 to 1. I don't want it to be below 0 or above 1. So I just clip them by value. And the TensorFlow has a very neat function, a very neat implementation provided. So I use that. Right? Just these 5 lines you add in your conventional or autoencoders, and you have your denoising autoencoders, right? And everything else is the same as the previous convolutional autoencoders. So like I said, it's just going to be a small delta on top of the convolutional autoencoders, right? Let's move on to the most important part, which is the convolutional variational autoencoder. Everything is the same here. There, everything is basically the same except two things. One, the bottleneck layer. Two, the loss function. First, we're going to see what's the difference in the bottleneck layer. If you see, if you've noticed in the previous example, the bottleneck layer was just a simple dense layer or a simple convolutional layer. Here, I have two max pooling layers. Now, one particular layer is the mu, which is the mean, and the other layer is the sigma. So what we're going to do in the encoder part is that we're going to do the same thing. We're going to downsample our input, make mean, and then what we're going to do in this part is we're going to compute these two layers, the mu and the sigma. I'm going to call them mu and sigma from now on. But in the decoder part, I'm going to do exactly the same as uh, the how do you say as I was doing previously in the convolutional neural autoencoders, right? But how am I going to call them? I'm going to call them like this. I call the encoder part, which runs this entire thing. Now it returns me two things: the mu and the sigma. Then I'm going to sample from this mu and sigma. And how I'm going to do that? I'm going to sample the epsilon, and the epsilon is a random normal, and from the sigma I'm going to compute standard deviation. And this is the formula that I've shown you in my blog, which is basically this thing. I'm going to compute this formula. Where is it? This particular formula, right? And I'm going to return that and give that output to the input of decoder, and that's how I compute and that's how I sample from mu and sigma, right? The loss function, the second difference is the loss function. The loss function is a mean squared error loss, which is uh, this particular part, and the KL divergence part, right? The KL divergence part is for computing or comparing between different uh, distributions, right? The The gradient computing part is exactly the same, except for two things. It's going to now return me the mu and sigma 2, right? The This part is exactly the same. I'm loading the MNIST data set. I'm training the oh I'm sorry I'm mean normalizing the training data set and the test data set, and then I'm reshaping them to the shape that I want. I've initialized my object from the class I've made, and I've also initialized an optimizer. Again, I'm going to use the Adam optimizer, but with 1e-3 learning rate. The number of epochs is 1 and the batch size is 1. Oh, the number of epochs is 50 and the batch size is 1. You can select it to any batch size. It's your own experiment to play with, right? Now, again, I am uh, the training loop is very similar to that of the convolutional neural networks. It's just that it's going to apply gradients to these to the trainable variables, which also include this mu and sigma, right? And everything else is similar to a convolutional neural network. So this is basically the entire code part of the autoencoders. Uh, I'm going to open myself to questions now. If anyone has any, uh, I think let me see. I'm going to open the Facebook live session and see if I have questions. Uh,
Hi, Imran. So, if in case any question comes in, you will be able to see from both our platform, Facebook and YouTube.
uh,
So we can wait if there are any questions. I can even flash them on the screen for you.
okay, thanks you. Thank you.
Hi, Imran. So, if in case any question comes in, you will be able to see. So I think the audience does not have any question right now.
Okay. Yeah, I can see that. I can see the YouTube and the Facebook. I don't see any questions here.
Although we have some feedback coming in from Ivan William.
Oh, what you saying? Oh, thank you, Ivan. I'm glad you could join.
So, Imran, if you
Yeah.
would like, we can conclude the session.
Yeah, I think that's about it from my end. And for all the listeners, I'm thankful to you guys. If you have any questions, you can share them on the YouTube or the Facebook, and I'll see to it and I'll answer any of it.
Yeah, in case you post any questions, you can inbox us either on the YouTube comments or even on the Facebook page or even the event page, and then we can relay it directly to Imran, and then he can be in touch. Don't forget to leave any of your contact details so that Imran can get back to you.
Yeah,
Imran, if you can kindly share the link of your blog right
sure.
now in the private window. So I will just flash it over here and even share it with the audience in the comments as well.
All right. Uh, should be okay. How do I see that? Uh, hmm. Okay, let me just stop my sharing and I'll share the.
Yeah, I've removed it from the stream. You can just use
Okay.
the screen freely. So, audience, we would like to hear your feedback, be it in the form of comments or be it in the form of private messages that you can relay to our GDG Cloud Islamabad page, and then we can relay all of that feedback, all of those comments, and all of those questions directly to Imran.
Yeah,
Um,
I've just shared the links, the both GitHub link and the Medium link.
all right, all right. You have shared it on Facebook.
Yep.
All right, all right. Yeah, they have been posted. All right. Thank you very much, Imran. Thank you, audience, as well,
Thank you.
for taking the time out for this interesting session as well. So, right now we have a very small announcement that we do have the Dev Fest coming up in the mid of October. So, we would like everybody here to join us there as well. There will be lots of workshops and live webinars as well from local as well as international people, as well as people from Google as well. So if you have any special request that if there is any topic that you would like GDG Cloud to specifically cover in those webinars, do let us know either through our page or through our YouTube channel. All right. Thank you very much. Thank you, Imran.
You're welcome, Roshan.
You're
Thank you.
taking the break after the long workshop. Thank you.
Bye.
Thank you very much, everybody.
All right. See ya.